Hey guys, this is 6.6. We're finally solving exponential and logarithmic equations. So a couple of definitions and properties to look at first. From the definition of logarithms, we can conclude the following. For a greater than 0 and a not equal to 1, a to the power of log base a of x equals x. So what that's saying is that the log base a and your base a here cancel and you're left with x. Think about why this makes sense. Let's try converting this to log form, right? This would be log base a because the base of your exponent is a, so log base a of x equals the exponent log base a of x. Right? Log base a of x equals log base a of x, obviously true. So that's why that property works. All right, and log base a of a to the x equals just x. So that's saying that log base a and a are canceling and you're just left with the x. That is the exponent. Now to think about why that's true, use your properties of logs. Bring this x to the coefficient. Now remember, this is saying a to what power equals a, and we know that equals 1. So it's saying x times 1 equals x, or x equals x. So that's why those properties hold. So you can use these properties in solving log equations by you can get rid of a log base a by raising both sides or putting both sides to the base of a. And then also you can get rid of, or you can bring an x out of a denominator by taking the log base a of both sides. Okay, and then another property of logarithms. If x is greater than 0, y is greater than 0, and a is greater than 0, and a does not equal 1, then the following holds. So all that's saying is x and y have to be greater than 0 because you are taking the log of those numbers. And then also a is greater than 0, a cannot equal 1, because that is your base on your log, and we know that has to be a positive number not equal to 1. Okay, but here's the property that we need to know. If x equals y, then log base a of x equals log base a of y. So that's saying you can take the log of both sides of an equation and it's still going to be equivalent. It's also saying that if you have the log base a on both sides of an equation like this, then what's inside of those logs, x and y, must be equal. It goes both directions. So you can also use that to solve equations as well. All right, so let's get into solving. First, we're going to start with solving exponential equations. So there are multiple ways to solve these, and so I will be showing you more than one option. So for this first one, 3 to the power of x equals 27. One way that you can solve this is by changing the base of this side to be 3. How can I make 27 into a 3? Well, 3 cubed equals 27. So we can replace 27 with 3 cubed. And now, similar to this property here, if 3 to the x equals 3 cubed, then x must be 3. So then you can just set those exponents equal to each other. And you've got your x. Not sure why I just erased that. Okay. So by changing the bases to match, then you can just set your exponents equal to each other. Another way that you can solve this one, 3 to the x equals 27, is you can actually take the log base 3 of both sides. So that would be using both of these properties. So if I take the log base 3, because that would match my base, then it's going to cancel that 3 out. And also that uses this property of logs, saying that you can take the log of both sides and it's still going to be equivalent. All right, so taking the log base 3 of both sides leaves me with x equals log base 3 of 27. Well, you should know what log base 3 of 27 is, because that's saying 3 to what power equals 27, and that would be 3. So either way, you get 3. Either changing the bases to match or taking the log base 3 of both sides to get that x out of the exponent. All right, let's look at B. Okay, I'm going to use that first option here, and I'm going to change this right-hand side until I get a base of 4 on my exponent, right? If I get those bases to match, then I can set the exponents equal to each other. So first thing I want to do is change that cube root to a 1/3. 16 to the 1/3. And then I also know that if I want to move this out of the denominator, I can make the exponent negative. So that will be 16 to the negative 1/3. All right, and now since 4 squared is 16, I can change the 16 to 4 squared. So I have 4 to the x equals 4 squared to the negative 1/3. Just changing the 16 to a 4 squared, since those are equivalent. Now, a power to a power you would multiply, so that's 4 to the x equals 4 to the negative 2/3. And since our bases match, you've got x equals negative 2/3. So a little bit more work on that one to get the bases to match, but doable, right? We just changed that cube root to the exponent 1/3, made the exponent negative to move it up, changed 16 to 4 squared, and we were ready to solve. It's not as pleasant on this one to take the log base 4 of both sides, in my opinion. Taking the log base 4 is going to cancel that, and yeah, I'll leave you with log base 4 of all of this, but that would still be a little tricky to figure out what log base 4 of that fraction is. So that's just this is a good strategy to use on problems like this, especially if you're in a situation where you can't use a calculator, right? If you're able to change the bases to match and then set the exponents equal, then you can solve the equation. All right, now let's look at some where you can't do that, where you can't change the bases to match and use that strategy. So what I would do here, because I can't make 21 match 8, there's no way to raise a number to some power to get 21 so that your base is 8. So that's not going to work. Can't get those two bases to match. So what I would do here is take the log base 8 of both sides. Here, I'll write that underneath. Log base 8 of 8 to the x, log base 8 of 21. So now using our property of logs, a power property, that x can come down, and we have log base 8 of 8 equals log base 8 of 21. These cancel, so x equals log base 8 of 21. Now you can do that in your calculator. Log base 8, if you hit math, scroll up, log base is right there unless it's been disabled on your calculator. So I can do log base 8 of 21. So we're rounding, let's see what it says to round to, nearest thousandth. So that's 3 decimal places. So your answer would be 1.464. Approximately 1.464. Now, if you don't have that log base in your calculator, or if you just want to do it a different way, you can just take the log base 10 of both sides or ln of both sides, either one. So you could do ln of 8 to the power of x equals ln of 21. You can still bring that x down. But now ln of 8 does not cancel. That does not equal 1. So you're going to have to divide by ln of 8. So x equals ln 21 over ln 8. Like I said, you can use log base 10 or ln, either one, because both of them are in your calculator. And so now your answer, ln of 21 divided by ln of 8. And it would be the same thing if you did log base 10. 1.464. So you can do it either way. Use the same base and then it's going to cancel. But you can also just do log base 10 or ln and then divide. All right, let's look at D. So on D, notice that your base on each side is actually two different numbers. So again, you could do log base 5 or log base 8 of both sides, and one of your bases would get to cancel. I'm just going to take the log base 10 of both sides to get those exponents out of the x's out of the exponents. That's why we do this. That's why we take the log of both sides, because we need to get those x's out of the exponent. So log base 10, that allows me to bring the 2x plus minus 3 down. So 2x minus 3 parentheses, because that log base 5 should distribute to both if you were going to distribute. Same thing with the x plus 1, but that in parentheses. All right, now we're solving for x. So what I would do next is distribute both of those. So 2x log 5 minus 3 log 5. I don't know why my pinky or something keeps writing on the board. Minus 3 log 5. And then x log 8 plus log 8. Now I'm going to move everything that has an x to one side and everything that does not have an x to the other side. So I'm going to move this x log 8 over here to be with the 2x log 5. So that's minus x log 8. Add the 3 log 5 to the other side. Okay, so now everything that has an x is on the left, everything that does not have an x is on the right. I'm going to factor the x out right here as a GCF, so x comes out. I'm left with 2 log 5 minus log 8. And then I can divide. I can divide by this to be left with just x. So x equals 3 log 5 plus log 8 divided by 2 log 5 minus log 8. Okay, and then we need to type that into our calculator to get the decimal. So 3 log 5 plus log 8, and I'm going to just hit enter there. So that's my numerator, and then 2 log 5 minus log 8. Okay, that's my denominator, so I don't really need to scroll up to grab 3. But 3 divided by, and then scroll up to get that exact value. So 6.062 if we're rounding, so approximately 6.062. All right, yeah, that one was a little challenging, but doable, right? We took the log of both sides to get those exponents down, and then we distributed our logs, moved the terms that have an x to one side, and we factored those x's out so that we could divide by what was remaining. And that gave us our answer. All right, let's try some with the base e, some exponential equations with base e. All right, so again, to get that x out of the exponent, we want to take the log of both sides in some way or another. Now, since it's base e, why don't we take the ln of both sides so that ln of e will cancel using this property here. If I take the log base e of e, you're going to just be left with the exponent. So I'm going to do ln of e to the absolute value of x. What you do to one side, you have to do to the other, so take ln of both sides. Okay, ln of e is going to cancel. I'm left with just absolute value of x equals ln 50. Now, how do we solve absolute value equations? You might need a little refresher on that. What you do once you have the absolute value by itself like this, you're going to split it into two equations, one with a positive of this side and one with the negative. So that's going to be x equals ln 50 and x equals negative ln 50. Rounding to the nearest thousandth, so let's get ln 50 in our calculator. Okay, 3.912. So x equals positive and negative 3.912. Positive or negative 3.912. All right, on B, you don't want to just go ahead and take the ln of both sides here because you have this 5 in the way and you also have two different e's on the left side. So let's see if we can simplify this a little bit first. What if I combine these two by adding their exponents, right? When you're multiplying two things with the same base, you can add the exponents. So that's going to be e to the 5x minus 1. Okay, and then now let's take the ln of both sides. Now we can take that ln, because now we can bring that exponent down and cancel ln of e. So 5x minus 1 equals ln of 5e. If you wanted to, you could take it a step further here on the right hand side and use your properties of exponents to split that. So that'd be ln of 5 plus ln of e, which we know ln of e equals 1. So this is 5x minus 1 equals ln 5 plus 1. Now solving for x, I would add the 1 over and then divide by 5. That 2 is not inside that ln, just like the 1 was not inside the ln. Then I'm dividing that by 5. And then I can type that into my calculator to get the answer. Now you didn't have to necessarily split this up because you can type this into your calculator as well. But if you didn't have a calculator or you needed to split it up for some reason, you could use that property. All right, so ln of 5 plus 2 divided by 5. If you did not do that in two separate steps, you would need to put this part in parentheses to make sure it adds those together first, and then divide by 5. If you're wondering why you didn't get the same answer, maybe you didn't put that in parentheses. Okay, so this is approximately 0.722. we've got one more problem to do in part 1. So this is going to be solving something that's in quadratic in form. So looking at this equation, you may notice that it kind of looks like a quadratic. You've got this squared here in the first term, not in the second term, and then there's no e to the x at all in the third term. So what I would do here is rewrite this as a quadratic. Two ways you can do this. You can change this e to the x to e to the 2x to e to the x squared. Like that. And then if you can recognize from there that that is quadratic, you can just leave it at that and start factoring to solve. Option 2, you could substitute some letter like u or y or whatever makes you feel more comfortable, but typically u is the letter used for substitution. You could substitute u in for u to the x, for e to the x, and here's what that would look like. So I'm saying u equals e to the x, so this would be u squared minus 6u plus 5 equals 0. Okay, so now we can factor that. Two numbers that add to -6 and multiply to 5 are going to be -5 and -1. So u minus 5, u minus 1. Okay, so u minus 5 equals 0, u minus 1 equals 0, gives us u equals 5 and u equals 1. But we're not solving for u, we're solving for x. So remember, u was e to the x. And now we can get our two equations by solving those two exponential equations. Okay, so I would just take the ln of both sides because my base is e, and I know that that means those are going to cancel. So x equals ln of 5. And over here, same thing. My base is e, so why don't I just take log base e? So x equals ln of 1. Now let's get those two values. So ln of 5, I'll get in my calculator. 1.609. Okay, and ln of 1, so e to the what equals 1, and that's 0. Remember, anytime you take the log of 1, it is 0. So that one equals 0. You could also get that in your calculator if you forgot. You get 0. Okay, so two solutions because it was quadratic, and those are them. Those are those two solutions. All right, we will continue these notes in part 2. Sure, you do some sort of practice on this. It's going to take some practice to get good at solving these equations. All right, so make sure you do the OpenStax practice. Do some practice, especially before that homework check tomorrow.